Good morning everyone, Dr. Nat here. We are doing chapter 6 today, which is uniform circular motion. We have 3 parts to this chapter, which is uniform circular motion, examples of it, and Newton's law of gravitation. So for today's video, we are doing the introduction on uniform circular motion. So let's do this. Okay, so uniform circular motion is when a body revolves in a circular path. So I have a circular path. This is my circular path with its center somewhere outside the body. For example, I have a string. And a ball is connected to it, and the ball moves in this circular path, but the center of rotation is here, right? The center of rotation is here. And if we were to look at this Ferris wheel, it is rotating like so, and it makes one complete revolution when it ends up at the same initial position. That's one revolution. And the center of rotation is here. That is why we have these strings of metal. Well, I don't think it's a string, but you have something looking like a string connected to these cars, right? To make the Ferris wheel. So the center of rotation is at the center outside of the body. It is at the center of the circular path. So again, the circular path is here. The circular path of the electron is here. The center is here. Imagine a string. This is your electron. This is your circular path. So center is here. And imagine your Earth. Our Earth is the ball. We have a string. It's moving this way. This is the center of rotation. So center of rotation is outside the body. Alright? Now, circular motion is a motion in 2 dimensions. So, for example, I have a ball connected to a string. This is my center of rotation. And my ball moves in this circular path. So each time it moves in this circular path, for example, moves here, in this circular path, the direction of velocity keeps on changing. The direction of velocity keeps on changing. Okay? So, if someone were to ask me, what is the direction of velocity at this point, Dr. Nat? So I would have to resolve it. Say, oh, Vx is 10, Vy is 20, so this gives me a V of angle, I don't know, something. And then I have to resolve this guy, I have to resolve this guy just to describe the velocity, because I don't know what angle it is actually at. So to solve this, to make life easier, they described angular velocity. They come up with angular velocity given by this omega. This guy is called an omega, which is a Greek letter. It's a Greek letter. Okay. So omega describes angular velocity. What is angular velocity? It is the change in theta, or the change in angle over the change in time, which means that this guy is delta final minus, this is theta final minus theta initial over time final minus time initial. Right? Because that is what delta means. Final minus initial. How do we know what angular velocity is? So, we will talk more on this in the next slide or in the next few slides. So, what you have to take from this slide though is we are describing circular motion in angular velocity because it is difficult to describe the x and y components each time it rotates. Okay? The direction of velocity is constant in magnitude and is always tangential to the circle. What on earth is tangential? Tangential is it moves in a straight, it is a straight line basically. So, for example, this guy is moving this way, right? The circular motion is this way. So the velocity, you know that the velocity is tangential. So if I am interested in this point, what is the velocity at this point? the arrow should be like this, touching the surface that we are interested in. So this is my V tangential. And what if I'm interested here? So the V is touching the surface that I'm interested in, or the point that I'm interested in, and this is the direction of my V tangential. It's downwards. And the direction of V tangential over here is to the right. So here we know that V tangential is always constant in magnitude, but the direction always changes. So V tangential has same magnitude, right? But different direction. Which is why we came up with omega to solve it. So tangential velocity, or V tangential, same thing, can be related to angular velocity omega by the following equation. Omega equals to 1 over r V tangential, or V tangential equals to r omega. R is the radius of the circular path. Circular path. For example, the radius of this circular path is from the center to here. That is your R. Okay? Okay, so far we have learned about omega, which is delta theta over delta t. And the unit is radian per second. And then we learned about V tangential, okay, which is a linear velocity. And we related these two by V r omega, where r is the radius. We have two different notations now. We have two new notations, which is t, it's called period, and f is frequency. Okay, so what are these two things? So I have one circular path over here. I start at this position and I rotate and I come back to this position again, right? So this was my initial, and my final position was this guy again. So I completed one circle, one completed circle. This complete rotation, or this one complete circle, is called one revolution or one cycle. And the time taken to complete one revolution is known as t, period. So let's say for me to complete one whole rotation or one complete circle, it took me 1 minute, right? So my t is 1 minute. What is the frequency? Frequency is 1 over t. So this is just 1 revolution per minute is my frequency. So this becomes 1 revolution per minute. So it's 1 revolution per minute is my frequency. So revolutions per minute, you can write it as RPM, where R is revolution, minute is M, and P is per. Another unit for frequency is CPS, which is cycle per second. Okay, so C is cycle, S is second, P is per. Okay, so those are the two units for frequency, and you have angular velocity with radians per second. Sometimes they will tell you the angular velocity of this ball is 5 revolutions per minute. Actually, angular velocity and frequency are interrelated in a sense that they measure the amount of rotation per time. It's just a matter of understanding how to use the units. Okay, we will take a look at an example later. Don't worry about that. So to test our understanding of what we have learned so far, let's do this question. Convert 48 degrees to radians. Okay, so remember, we have, in a full circle, we have 360 degrees, which is also equal to 2 pi radians, right? So to convert degrees to radians, so this is degrees, I want to get rid of my degrees. So the degrees should be below here and the radians should be above. And then I can cancel out degrees to give me the answer for this question, which is 0.84 units. I'm left with radians now. Okay, so that is part A. So part B, 16 radians to revolution. Right, so how do we convert radians to revolution? So 1 revolution or 1 complete circle equals to 2 pi radians, right? Okay, so how do we do this? 16 radians. We want to get rid of radians, so radians should be below, should be the denominator. So, sorry. So that is a 2 pi radian. And 1 revolution should be on top because we want the revolution. So radian cancels out with radian. So this will give me an answer of 2.55 revolution. Okay, I can write revolution as REV. That's fine. So that is B. So question. So we want to convert 78. Oh, I don't like this color. Can't see. So let's use pink. So 78 RPM. What is RPM? It's revolutions per minute. So let me write that like this so that it's easier for me. So I want to get rid of revolutions and convert it to radians. And I want to get rid of minutes and convert it to seconds. Okay, let's do the easiest one first. So how do I change minute to seconds? So 1 minute, I want to get rid of minutes, so it should be on top. Divided by 60 seconds because 1 minute equals to 60 seconds and I want my seconds. So now I can get rid of minute. I'm left with seconds. How do I change my revolution? I want to get rid of revolution, so it should be below. 1 revolution equals to 2 pi radians, right? So now I can cross out revolution. Now I'm left with radians and seconds. So this will give me an answer of 78 divided by 60 times with 2 pi, or you can just give me the answer straight away, which is 8.17 radians per second, right? I'm left with radians and I'm left with second. So that gives me a unit of radians per second. Alright, so this is the end of part 1. In part 2, we'll take a look at what centripetal acceleration is. See ya!